Hello everyone, and thanks to you all for joining us in this, which is the 10th of our series of webinars that discusses LimitState products, their features and their applications. For those of you who haven't attended one of our previous webinars, my name is Tom Pritchard and I will be the host for today's event. We'll introduce you to our speaker shortly and also round up at the end. So today's webinar is entitled Modelling Soil Reinforcement with LimitState GEO, and it's going to discuss LimitState GEO's engineered element material and how it can be applied to a wide range of soil reinforcement problems such as soil nails and geotextiles. The main part of the webinar itself will run until approximately 10 AM UK time, so for about 50 or 55 minutes, and will include about 10 minutes at the end for questions. These can be posted via the chat functionality that's present in the webinar interface in front of you. We do try and answer as many of the questions as we can in the time that we have available, but sometimes this isn't always possible. So I do apologise in advance if we're unable to get round to your questions. But we do, after the webinar, we will follow up on anything that we have not answered during the webinar itself. So as always, I'd just like to ask if anyone has some very, very specific questions regarding the software which may require a long or quite considered answer, please do contact us outside the webinar via info@limitstate.com and we'll be more than happy to answer these in detail for you. So without further delay, our speaker for today is Dr. Colin Smith, who is the LimitState GEO Product Manager, and I'll now pass you over to him.
Okay, thank you, Tom. Good morning to those of you in the European time zone, and good afternoon or evening to those of you joining us from elsewhere in the world. As mentioned today, my aim is to show you how LimitState GEO can be used to solve reinforced soil problems, how it differs from other methods, and how to model a number of specific scenarios. To this end, I'll be using a mix of slides and the software to illustrate the key points. As you can see from the contents page, we'll start off looking at some background theory before looking at how the software can be used to model reinforced soils. So as this is a problem-specific webinar, I'll focus on how to use the software to solve soil reinforcement problems, so I may therefore skip over some of the basic details of how to use the software, but hopefully the process should be clear. Now, for those of you who are new to this webinar series, I think it's useful to first give a little bit of context to the software and to the company LimitState. The University of Sheffield has been conducting research into limit state analysis and design and use of optimization in civil engineering for almost 2 decades now. And the company LimitState was spun out from the University of Sheffield in 2006 with the aim of making this research available to industry. As industry users, you want not only powerful tools, but of course ease of use and support, which is exactly what LimitState is able to provide. It's also got sophisticated testing systems in place that mean every time the software is changed, almost 1,000 tests are automatically run to ensure that the software continues to do what it's supposed to do. The company has 3 products at present: LimitState Ring, LimitState GEO, and LimitState Slab, with several more in the pipeline. And the products are used by a range of companies, large and small, in over 30 countries worldwide. Now, to set LimitState GEO in the context of currently available software, on the one hand, at the top left here, we have software based on conventional approaches, such as the method of slices, which do a pretty good job specifically for slope problems. For more complex analysis, finer element software is available, which can model pretty much any geometry and complex soil behavior, but typically requires a lot more expertise to use. There's a gap between these 2 tools, and we feel filling the gap is computational limit analysis. Now, this provides the geometry flexibility of finer elements with the ease of use and simplicity of the traditional methods. The only parameters you require are cohesion, friction, and self-weight, essentially, of soils. And this is what LimitState GEO provides. Similar approach can be used in other engineering applications, such as arch bridges and concrete slab analysis. Now, in geotechnics, such approach allows LimitState GEO to determine the collapse state for any problem geometry. It's able to model slopes, retaining walls, structural elements, and soil reinforcement, as shown by some of these examples. And our aim today, of course, is to focus on soil reinforcement analysis. So just a little bit of recap of some of the basic theory so that we can see how that's implemented in LimitState GEO. So soil reinforcement works primarily by adding tensile strength to the soil, or equivalently transmitting tensile stresses from one part of the soil body to another. And reinforcement may be one-dimensional, such as soil nails, or two-dimensional, such as geogrids or geotextiles. So there's a range of different reinforcement types, and LimitState GEO has been set up that it can model either the 1D or the 2D type of reinforcement. And of course there are a large range of applications for soil reinforcement. I'll just show 3 examples here that you can model with the software. Now, in terms of classical analytical approaches, we have limit equilibrium. In this case, we assume a slip surface. So if we're looking at the diagram on the top right, maybe a curved slip surface, and we might analyze that by method of slices, looking at equilibrium of slices. In the bottom diagram, if we've got reinforcement in the slope, then for failure to occur, either the reinforcement has to pull out of the sliding mass, or it has to pull out of the stationary mass on the right hand side here. And if we can work out, if we know the shear resistance around the reinforcement, we can calculate a pull-out force, and this additional pull-out force T can then be applied to our slip circle analysis and enhance the stability of the slope. For steeper slopes, or indeed an alternative method of analysis, we can use perhaps single wedges or 2 wedges, and the principles are very similar. Rather than using a curved surface, we just used a wedge, but equally well we apply these restraining forces to the reinforcement pull-out to enhance their stability. In terms of the detail of how we calculate those forces, for an undrained soil, typically we're going to assume that the shear stress at failure on the reinforcement boundary is some factor alpha multiplied by the undrained shear strength of the soil. And for two-dimensional reinforcement, the pull-out force per unit width is going to be twice alpha Cu times the length of the reinforcement. And we multiply by 2 because, of course, we've got shearing on the top and the bottom of the reinforcement. If we're looking at one-dimensional reinforcement, then we just need to work out the circumference or the surface area of that reinforcement. So typically, for a soil nail of diameter D, we'd have pi d for the circumference, again multiplied by the length, alpha, and Cu. And what we can see that in both cases, this boils down to some constant Tc multiplied by the length. And Tc is a number that we actually would enter into the software. We'll come to that a little bit later. In terms of drained case, it's a little bit more complicated. This time we assume that the shear stress at failure on the reinforcement is again some coefficient alpha multiplied by the average normal stress on the reinforcement multiplied by tan phi dashed. And again, we can calculate this for 2D cases, multiplying that by 2 for the upper and lower faces, or for one-dimensional, say, cylindrical reinforcement, where we multiply by the circumference. For the second case, or indeed for the first case, estimating this average normal stress is a challenge in terms of limit equilibrium. A typical common assumption is just to assume that the normal stress is the nominal vertical stress at that point, which we calculate from simple statics. And the software can be set up to do that. And for cylindrical reinforcement, of course, the lateral stresses will vary around the reinforcement, and again, there is guidance in the literature, but essentially we can say it's some constant multiplied by the prevailing vertical stress. In either case, the pull-out force is essentially some constant TQ multiplied by the vertical stress and the length. And again, TQ is something we can therefore calculate and feed into the software. Okay, so that's a little background to soil reinforcement. Before we look at how that's modeled in LimitState GEO, we actually use the software. It's helpful just to recap on how the software itself works so we can put that into context. So the software uses a method called discontinuity layout optimization to provide plasticity solutions for collapse. It's a direct way of analyzing the collapse state, and was the outcome of a 5-year EPSRC funded research project at the University of Sheffield. The core method was published in 2007 in the Proceedings of the Royal Society, but it's relatively easy to describe the core process. So if we take an example of a block of soil here, and with a surface load and fixed boundaries to the left and to the base, unlike finite element methods, what we do is we populate the domain with nodes. So here I've got 12 nodes, and we connect every node to every other node with a potential slip line. So in this case, that's 12 times 11 over 2, so that's 66 potential slip lines. Then what we do is we feed all those potential slip lines, formulate that as a linear optimization problem, feed it into a powerful optimizer, and what that does is it picks out the key slip lines that form the critical mechanism that dissipates the least energy. So in this case, out of those 66 lines, we pick out 6 slip lines that form the critical collapse mechanism. Now, of course, when we actually use the software, we may be working with 500, 1,000, 2,000 nodes. So that's of the order of 1 million potential slip lines, and the software is rapidly able to pick out of that 1 million the critical collapse mechanism. So the more nodes you have, the richer the set of slip lines that the software can pick out of, but essentially it's able to pick out very complex mechanisms from that. Once we've found the critical mechanism, the software actually stitches all those slip lines into solid elements or wedges and can animate those to help interpretation. As I said, increasing the number of nodes allows more potential slip lines, and there's a more precise mechanism to be identified. In terms of soil reinforcement, we can model reinforcement elements within the soil body that will interact with these sliding wedges, but in a very, very general way. So, for example, at the top right here, you can see the green reinforcement is actually pulling out of the soil in this animation. So there's pullout going on in that point. To the top left, we've got various wedges, so actually there's different relative movement between the soil and the reinforcement, but the software can handle that in a fully general way. And down here at the bottom, we can actually see that the reinforcement which has been embedded in the wall element is pulling out in this case. So all types of failure modes can be modeled, sort of classical pullout, and also more complex interaction. And so if we have any mechanism or any sliding wedges, it's quite straightforward to work out the forces acting between the reinforcement and the soil. In essence, the shear force is going to be the area of unit reinforcement per unit length, that's unit length into the diagram, multiplied by the length of the element of interest, and then we're either going to have a frictional or a cohesive element to that. So essentially, it boils down to an equation here where the shear force or interaction between the reinforcement and the soil is the length multiplied by a coefficient TQ multiplied by the average prevailing normal stress plus another coefficient to do with the cohesion. And formulating it this way means we can provide a very general implementation of soil reinforcement interaction, and there's no need to consider things like pull out, which parts are stationary, etc. Now, just to clarify that equation, essentially, it's best perhaps to use the software to illustrate those, so we get those terms clear. So what I'm going to do is just start up the software and the first example, which will be that one. So here we have a simple pull-out test, so it's really an element test. Having started up software, for those of you who haven't seen the software, I'll just quickly discuss the layout. So basically, the main screen here shows the problem. We have buttons along the top to control display and solution of the problem. Down the left controls drawing or manipulation of the geometry. Key point here on the right hand side is we have a property editor. Anything I click on in the problem, its properties appear on the top right, and down here we have a geometry editor. Its geometry appears here. So what essentially we're modeling here is a rigid block on the left, which just has some reinforcement embedded in it, and this red line in the middle here is a block of, is a reinforcement element embedded in a body of soil, this sort of pink colored material. If I click on that material, oops, it's highlighted and its properties appear on the right. What we're interested in is what material it contains. It contains a soft clay, and the key thing here for this example is that the undrained shear strength is 30 kPa. If I click on the reinforcement itself, so I've missed, there we go, its properties appear. We term any reinforcement element in the software an engineered element. It can model reinforcement. We can also use the same engineered element to model, for example, sheet pile walls. But in this case, we have one engineered element, and it's called reinforcement 2. And the key point here is that we're modeling a one-dimensional element like a soil nail, and it has a pull-out factor 10. I'll just move these boundaries back a bit. Okay, so in this one we've set up a value of TC to 10. So basically it's in a cohesive soil, and we're saying that it requires 10 kilonewtons per meter squared force per unit length of reinforcement to pull that element out. So to solve the problem, I simply click this button, which is solve, and what it's going to do is tell me the force required to pull that element out. Now I've configured it in such a way that the answer that comes out is directly in kilonewtons per meter length into the diagram. So if I click solve, software quickly works out what's happening. Of course, it's a very simple collapse. All we're doing is pulling this element out. You can see it pulling out there, and we have what's called the adequacy on load of 20. That, in the context of this problem, is a force of 20 kilonewtons per meter width into the diagram is required to pull that out. So that 20 is what we'd expect. If I unlock the project, set it back to where it was, if we recall, the pull-out force was 10, and the length of this element, its geometry is given down here. It actually runs from 2 to 4, so it's 2 meters long, and therefore the pull-out force should be 2 times 10, which is 20, which is what we expect. The software also displays the predicted tensile force in the element, so we can see that this graph here shows the tensile force in the element building up from this end, the free end, where it's obviously going to be 0, right up to when it's connected to this rigid block where it hits a full value of 20. Now, just to clarify, if I doubled that pull-out coefficient to 20, so it's 20 kilonewtons per meter length of the element, then we should get an answer of 40. So we'll solve again, and down here we can see that we get a result of 40. And if I increase it again, I'll increase that to 100. Now we might expect that we should get an answer of 200 in this case, but actually the software gives us an answer of 120. And that's because the software, it knows that we've told that it takes a force of 100 kilonewtons per meter width and per meter length to pull that out, but actually it also knows that this reinforcement is embedded in a soil, which if we look back has a shear strength of 30. So the maximum resistance we could possibly get out of an element, even if it was planar two-dimensional element, is that 30 multiplied by the length of the element 2 multiplied by 2 to cover the top and bottom surfaces, and that's 120. So the software is saying, actually, you've specified a pull-out force which is impossible, and that's the most you could possibly ever get out of it. So the software will always hunt the most critical failure mode, whether it's pull-out or it's actually shearing the surrounding soil directly. So that's why we get 120 rather than 100. But that shows the flexibility and the way the software can pick out the most critical mechanism. Finally, what I'll do is just illustrate rupture. So at the moment, we've specified a pull-out force for this reinforcement. Sometimes we might want to specify a rupture strength. So this is a force at which the reinforcement will effectively yield and start to stretch. At the moment we've set it to effectively infinity, 1E30. If I set that value to 60, then and then solve, what will happen is that, of course, we can get no more than a load of 60. Before we could get 120, but we can only get 60. And the stresses are building up along the boundary, but they hit 60 at the end. We can't go above that point. And essentially, the reinforcement stretches. So it doesn't pull out at this end, it just stretches because we've caused it to yield. So we can model rupture as well as pull out in these types of problems. So that's a quick introduction to pull out. If I model, just show some lateral effects. Now, generally with reinforcement, we model only tensile interaction and shear interaction, and generally ignore the lateral capacity. But if we have a soil nail or indeed a pile and we wish to look at its lateral capacity, piles obviously we consider their lateral capacity, trying to move a pile sideways through soil. Equally well, if soil is moving normal to a soil nail, we'd expect a little bit of resistance. Though typically that is ignored in conventional analysis. The software, however, is able to model that. You can easily set it to 0 if you don't want it to be modeled, but we can do that. And this model here, another element test, illustrates that. Effectively, we've got our reinforcement element here. Oops, I click on it, and its property, it has a lateral factor here of 25. So that means a force of 25 kilonewtons is required to push that sideways through soil per unit length of element. The element is 3 meters long. It runs from 1 to 4. So we would expect a capacity of 75 in this particular case. And we've basically set up some rigid elements here that will allow us to effectively push this element sideways through the soil. So if I click solve here, essentially you can see that the soil is being pushed through the element. Here we're actually displaying the shear force in the element, in the reinforcement, but the answer is 75. So that allows us to incorporate lateral capacity if we wish. Okay, so that's some background to the element tests. So that hopefully it clarifies how we use the software and specify numbers to look at pull-out and lateral capacity for one-dimensional reinforcement only. So in summary, we can assign frictional cohesive pull-out resistances per unit length for reinforcement. We're following the same mechanics principles as conventional analysis, and we can specify lateral resistance. Normally, in conventional analysis, that's set to 0. In the software, we would always advocate putting in a very small value, and that simply prevents floating of the reinforcement. If we put no lateral resistance in, then the software can say, well, the reinforcement has nothing to stop it just floating out of the ground. So a very small resistance will just prevent that. And we can specify tensile rupture strengths. So how can we use this? Well, we'll look at the example of a soil nail slope. So we'll pick a nail diameter of 0.25 meters, an interaction coefficient of 1, and a horizontal nail spacing of 1 meter. Take some soil properties. C dashed is 3.5, phi dash 26. So we can work out our value TC, which is the circumference of the nail multiplied by alpha C dashed divided by the spacing, this value, and TQ, which is a frictional component, by a similar calculation. So I've set that model up in the software, and let me just Find that one, yep. So that's the problem, and if I click on one of these items here, that's the soil nail, and you can see these properties that we specified for pullout. And you can see I've put a small lateral factor in 0.01 to stop them floating. And we've set the rupture strength to infinity, so we're not worrying about failure of that. So again, I just click solve, and in this case, the software identifies a failure mode down the front. So while it's also simultaneously trying all millions of different failure mechanisms, which include two wedge mechanisms that go further back, it's actually identified that this is the most critical failure mode for the parameters that we've set up. And we get an adequacy on load of 1 here. Now I need to explain a little bit more about this, how the software, what that number actually means. I skipped over it slightly previously. Effectively, we've got a problem here, and we're trying to work out its ultimate limit state. If we've designed it correctly, then it shouldn't be anywhere near its ultimate limit state, and we need to do something to get it to fail. And this is kind of implicit in any ultimate limit state calculation. We can do that in 2 ways. We can either increase a load somewhere until the system fails, or we can reduce the strength. For this example, I'm going to use the load method, and essentially what I've asked the software to do is increase the self-weight of all the soil in the problem up to the point at which collapse will occur. And that factor, that number by which we need to multiply the self-weight of the soil, let's just look at the soil. So if I click anywhere here, I can get the properties of the soil. It's got its C' of 3.5, 5, 26, and a unit weight of 17 in this case. So we're asking the software, how much bigger does that weight have to be to cause collapse? And that's one way of using the software. We'll look at the other way in another example in a little bit. So essentially, when I click solve, it's trying to find that number and find the critical collapse mechanism. And in this case, it's coming up with a number just slightly bigger than 1. So that actually means the system is on the point of failure, and we don't really have to do much to it at all for failure to occur in this particular mode. Now, we may say, okay, that's okay. Perhaps we're not using the full length of nails. Could we get away with slightly shorter nails? It's very easy to adjust geometry in this problem. You can just click and drag elements, or if you click on an element you want to change its coordinates to something exact, you can click on the geometry editor here down in the right hand side and move points. And so I could get a different geometry there, and I can click solve, and the software will look at that. So what you can see in this case is that my adequacy factor has actually dropped to 1/2. It's quite clear that the software has said, okay, it's going to be easiest for collapse if the wedge at the top actually goes outside these new short elements, and then sharply comes into the end here to minimize its interaction with the lower elements which have been left long. So actually it's quite clear that reducing that length is quite critical. So it's very easy in the software to play around with geometries. You can change the upper slope angle or whatever, and you'll get the same generic analysis will come through in the software, and it will pick out the critical collapse mechanism, whatever you've set up. So there it's clearly saying, I'm going to totally ignore the lower reinforcement, go around it, and in this case I've got a slightly higher adequacy factor, presumably because I've made the top of the slope a little bit shallower, changed some of the geometry. And the software is very flexible in that, in terms of changing materials, changing geometry, very interactive, and that's how it's designed to allow you to do what-if problems. There isn't so much time in this webinar to illustrate all those features, but hopefully that gives you a little flavor of what happens there. So just to kind of wrap up that little section on soil and slope, that example was adapted from one by a paper by Clark et al. In 2013, where they looked at different values of C'. They looked at 2-part wedge mechanisms initially the classical approach and plotted out strength profiles, and also it's possible to get the software, you can force it to model two wedge mechanisms if you really want to, so you can constrain it only to be able to model those, and the first part of the paper is able to show that the software is then replicating exactly the classical hand calculation, and then the second part of the paper showed that if you actually allow the software to find the critical mechanism, which might be a lot more complicated, a lot more slip lines, so for the parameter set that one of the parameter sets that were being looked at, get a more complicated mechanism, then the software was able to show that it could find more critical mechanisms below the two-part wedge mechanism analysis. So that pretty well covers what I want to say about one-dimensional reinforcement, so things like soil nails. The generic implementation of LimitState GEO allows soil essentially to flow past reinforcement. LimitState GEO is a plane strain two-dimensional analysis, but we can actually analyze these one-dimensional elements by putting in these pull-out and lateral factors. So soil can sort of flow past the reinforcement, but the reinforcement can still interact and transmit tensile forces. It's been calibrated against two-edge analysis, and the recommended approach is to use engineered elements in the software with specified pull-out coefficients, TC and TQ, depending on whether you've got cohesion or friction. A lateral coefficient, but often set to 0 if you want to follow conventional type modeling. You can specify a rupture strength if required, and we generally would not apply boundary or interfaces materials above and below the element. Now, I'll clarify what I mean by that by the next case, which is two-dimensional reinforcement. So we can use the same engineered element to look at 2D planar reinforcement. And effectively, we can use that element if we give it infinite lateral resistance, so we don't allow soil to flow past it. Obviously, soil can't flow past a sheet of geotextile or a sheet of steel. But to model a geotextile, we put in 0 bending strength. In the previous examples, we actually had infinite bending strength modeled for the soil nails. You can, in fact, model lower bending strength if you wish. There wasn't time to look at that. For 2D models, we can directly specify interface properties and allow for differential shearing above and below the reinforcement, and also model tensile rupture strength. So what I'll do is look at some element tests just to illustrate how the reinforcement is modeled, and we'll do that with the following model. So let me just pull that one up. Which is this one, yes. So this is very similar looking to the previous pull-out test, but we've set it up slightly differently. So the material here is clay, and actually all the materials we use in the software are also shown in what we call the Materials Explorer here, so we can define any material we like, use our own parameters. There's also a number of built-in soils with kind of default values that you can use for sort of parametric studies or trying to get a feel for a problem. But this clay here, essentially it's being modeled undrained, and it has an undrained shear strength of 50 kPa. And if I click on the reinforcement, what we've done here is we've specified the pull-out factors to be infinity. It doesn't, as long as we specify one of them, and the lateral factors to be infinity. So the pull-out factor for two-dimensional reinforcement, we really only need that parameter for one-dimensional reinforcement, so we just set it to infinity for 2D reinforcement. The lateral factor is set to infinity because we don't want soil to flow through the reinforcement. Technically, the moment of resistance should be 0. In this problem, it doesn't actually matter because it's a pull-out problem, and we've set an infinite rupture strength because we're not looking at that particular case at the moment. So essentially, this is going to interact as sheet reinforcement with the surrounding soil. The element itself is 1.5 meters long, runs from 2 to 3.5 meters in the X direction. and it's surrounded by a clay soil which has a strength of 50. So essentially we would expect a pull-out force of the length 1.5 times 2 to cover top and bottom of the reinforcement times 50. So that should come out as 150, which it does. And again, we can see it pulling out here, and the axial force is building up at the end here to 150 in the element. So that does as we expected. Now, of course, often we model planar reinforcement geotextiles. We don't assume full interaction, mobilization of the full strength of the soil on the interface between the reinforcement and the soil. So you'll see here that when I click on that body, I've got the engineered element in the middle, but I've also got the ability to specify top and bottom materials. And that means I can apply interface materials. Now I've pre-created some interface materials here. I've got interface above material, and this effectively has a alpha factor of 0.9, which is applied to its parent material, which is that clay soil that the element is embedded in. And I also have an interface below material, which, just for the sake of illustration, I've said has got a coefficient of 0.6. So what I'm going to do is click on this element here, and for the top element, if I click on this box here, I can get change, and I'm going to assign interface above material. And then if I click on that element again and click here, I'm going to assign interface below. And actually, if I zoom in on this, you can see now that that element has got a line above and below with the colors of those elements to show that they've been assigned. So if I then click solve in this problem, I get a lower answer of 112.5 as the pull-out load, so the axial force builds up to that. And that's what we'd expect. We've now got the same length of reinforcement, 1.5 meters, but this time the shear force or shear resistance on the top is 0.9 times 50, and on the bottom it's 0.6 times 50. So if you add all that up together, it comes up to 112.5. So we can control that, and what the software is able to do is it's essentially able to model that type of pull-out, but it can also model sliding failure on the top interface or sliding failure in the bottom interface, or any combination of those. So having looked at that briefly, we'll now look at an example of how we apply that in a practical problem. So we'll look at a reinforced embankment. So this is when you're constructing something over very soft soil. You may put a geotextile, some reinforcing layer on the top of that before you construct the embankment, which may be constructed out of stronger frictional soils. So the typical questions you might ask are: what slope angle is feasible? How strong should the embankment soil be? How high can the embankment be? What's the required rupture strength for the reinforcement? Common analysis, if you look in the literature, quite a few analyses listed that cover slip circle or method of slices. But of course these make some initial assumption about the nature of the failure mode and isn't able to capture all possible failure modes. If I just pull up now a model of the reinforcement embankment. So here is a model in the software of reinforcement embankment. We have here, if I click here, this is a reinforcement. So we have an engineered element, a geotextile here. All these factors are set to infinity. What we're interested in is 0 moment of resistance, so it's flexible. And we're setting a rupture strength of 25 there. And on the top, we've got a material assigned, which is the top boundary, which effectively is applying an alpha factor of 0.8 between it and the overlying soil here, which is modeled as a sand. So that's modeling with a small c dash to the 32 degree angle of friction. On the base, we've got a soft soil with a CU of 16. And if I just go back to the reinforcement, on the bottom, we've got a bottom boundary material, which effectively has an alpha factor of 0.8. And that's relative to this soft soil on the bottom of the reinforcement. Now, I said that we can ask the software two questions about an ultimate limit state analysis. How much bigger does a load have to be to cause collapse? We can also ask it, how much weaker does the soil have to be to cause collapse? And that is essentially giving you a factor of safety on strength. So here, these modes are changed up here, factor load or factor strength. So in this model, we're going to work on factor strength. So we're asking the software, how much, what do we have to divide the soil strength by for this system to collapse? So if I just click solve again, problem takes a little longer to iterate through the solutions for factor strength, but essentially what it's telling me is that this thing will stand up, but if I've got a margin or a factor of safety of 1.23 on soil strength, that's both the sand and the soft clay, before this thing will collapse, and I get a sort of slip circle type mechanism in place. And we can actually see that we're mobilizing the full axial force of the reinforcement, so it is actually rupturing or stretching in this particular case. If I was to employ a much stronger geotextile, for the sake of illustration, I'll just multiply that value by 10, so it's clearly not going to have an effect, and click solve. We can see how that influences the solution. And actually, by doing that for this particular parameter set, it actually means that the software finds that the deep-seated failure into the soft soil is not most critical, and actually just a slope failure of the embankment itself is critical, with a factor on strength of 1.43 down here. And the axial force is quite high here, but is below the 250. Now, if you were interested in what's the lowest value of axial force or rupture strength in the reinforcement that you can get away with before it starts to affect the result, then you really want to be analyzing a mechanism that involves the failure involves the reinforcement. In this case, the reinforcement is not involved in the failure, so these forces here are effectively credible stress states, but these stress states are non-unique. They're only unique where you've got failure. So the thing to do is to reduce the strength of the material down until we start seeing an impact on the strength here. So if I were to reduce that strength down to 150, I can see whether that's going to affect things. Sorry, yeah, 150. So I click solve again. See what it comes up with. So actually we've got the same failure mode and still a factor on strength of about 1.43, so that really hasn't had much impact. I think it's only when we get down to, say, 100 that the reinforcement starts to fail through yielding. So now the software's, it's found us that the factor on strength has not changed much, but now we're starting to yield the lower soil and start to put significant stresses into the reinforcement, and that's now limiting. And if we go down to, say, 50, we will see that at this stage the rupture strength has a significant effect. So now down to 1.3, and if I continue to lower that, then we'd get more interaction. What I'm going to do is just revert that back to 250, so it's very strong, and actually show some other failure modes. So this soft soil here, if I change its strength from 16 to 8, then what we get is very much a sort of squeezing failure mode, where effectively we're squeezing the soil here. So effectively it's like a kind of vertical compression almost, and just extrusion of this soil out sideways. And that's going to be quite difficult to model correctly using say a slip circle type method, which will overestimate the capacity. I should say that this symbol here down here denotes a symmetry boundary condition, so we're actually modeling half the embankment in this particular case. So just one other illustration. I'll revert that lower soil strength to 16 again, and just to show the effect of changing interface conditions. I'm going to change this top boundary condition to 0.2 from 0.8. Now that of course is highly unrealistic. You'd have to put in a very smooth interface there, but it's really just to show that when we solve that kind of problem, it will affect the failure mechanism at the top here. And now, rather than just failing right sort of adjacent to the slope, we've got a slightly deeper mechanism that's actually taking advantage of this weak interface and sliding along the base. Now, just for speed of solution, you'll see that the number of nodes I've used in this problem is not very dense. We still get some pretty good answers out of it, but normally I would be using more nodes than this to get a good accuracy of solution. And you can, as you increase the nodes, you'll find that at the point at which the answer doesn't change significantly, then effectively you've got the best answer that the software is going to generate for you. So that's an example of a reinforcement embankment with a two-dimensional planar reinforcement, which we can model using these engineered elements. So that pretty well takes us through towards the end of this webinar. Hopefully I've illustrated a number of aspects there. In terms of planar reinforcement, hopefully I've shown you this. We have a generic implementation that has been calibrated against method of slices and slip circle analysis. So a number of papers have been written looking at that and examining the comparisons. And generally, of course, the software will find more critical collapse mechanisms than conventional analysis. So when we're modeling, just to summarize, two-dimensional reinforcement, we set these pull-out coefficients and lateral coefficients effectively to infinity. We specify a tensile rupture strength if we want, and we can specify boundary materials above and below the reinforcement to effectively model appropriate alpha interface factors. I mentioned that a number of papers had looked at this, so this is just a list of some of the papers published recently in the last 3 or 4 years, actually, looking at using reinforced soil and using the software to look at particular design problems or design aspects or analytical issues. So broad range of papers in UK and American journals. So to summarize, what I hope I've done today is show you that reinforcement modeling in LimitState GEO uses the same mechanics as conventional methods, such as the two-wedge method, but effectively we can model thousands or millions of wedges rather than just one or two, but still preserve the same interaction mechanics. There's no need to separately consider internal-external failure or pull-out lengths or reinforcement rupture as separate problems, which is often what you have to do in conventional analysis. That's all taken care of in the one analysis. And the method automatically searches all possible failure modes every time you solve. So whatever is displayed is the most critical one, and you can assume that it has considered all the other ones, including ones that you may consider conventionally. And hopefully you've seen that we can very easily change the geometry of the problems. We can also change the loadings quite easily. There wasn't time to show that in this particular webinar. We can model one- and two-dimensional reinforcement. The one-dimensional modeling of reinforcement allows soil to flow past the reinforcement to try and preserve that one-dimensional interaction, whereas the 2D modeling of reinforcement separates the soil and allows different interface properties above and below the reinforcement. Overall, I hope you've seen, as we've used that software, that the software is very interactive and solves quickly. So many of our customers use it interactively to answer what-if type questions. and certainly find that it allows you to get a much better feel for the problem, to explore what are the key critical parameters that control failure. And that hopefully you've seen that this software, effectively, this one piece of software can solve any ULS problem type. And so there's no need to try and impose idealization or correction factors from solutions in the literature to get them to fit the sort of problem that you're looking at. Okay, so that's taken us to the end of the webinar. So at this stage we have about 10 minutes for questions, and I shall try and answer those. As I go along. Okay, so got a question: how do I set the lateral resistance for a geotextile? Do I make it infinite? So yeah, that's just, sorry, I shall bring up one of the other models. Let's bring that one up again. So when we're modeling a geotextile, yeah, we don't want the soil to be able to flow past or through it. So essentially, for any two-dimensional reinforcement, essentially we just set all these values, or at least one of each, to infinity. And in the software, we just use 1E30 is what we use for an infinite value, and that effectively tells the software that yeah, it's an infinite value. So these parameters here are only used to specify one-dimensional reinforcement like soil nails. If you're modeling two-dimensional reinforcement, you just set all those parameters to infinity. Okay, had a question: how do we model reinforcement attached to facing blocks? So again, if I bring up one of the previous example models, so a pull-out model. So here, what we were focusing on was a reinforcement at this point embedded in this soil, but that reinforcement is connected to another piece of reinforcement here, so that's another engineered element, reinforcement element 1, whereas this was reinforcement, we'd called it R2. And whenever you connect two engineered elements together, then they connect and they transmit normal shear and moments across their connection as appropriate. So effectively that element is connected to that one, but this one has different properties. This essentially we modeled with a pull-out factor of infinity. So that basically meant it's rigidly embedded in this grey material, and this grey material is actually a rigid material, so it will not fail. So essentially we've connected this reinforcement from the soil into a different reinforcement. We define a different material with infinite pull-out, and then it cannot pull out of this block, and it's rigidly attached. We can of course specify a lower pull-out load, so if you wanted the software to be able to model the capability of possibly the reinforcement pulling out of the facing element, then you can define that by changing this value. Okay, simple question. Is this presentation going to be available to download? Yes, it will go up on our website in the next day or two. So you will be able to download that and review that in more time at that point. Okay, how would you model anchor reinforcement with a concrete deadman? So this is actually in a sense another use of the engineered element. We can actually use the engineered element to model anchor tendons if we like. So what I'm going to do here is shorten that element. So I'm going to remove the material from that end, just untick it. So now I've got a shorter element here, and what I can do is embed. I can draw around it, so I'm using a polygon tool here. I just need to zoom in a bit. So very rough and ready here, but I'm drawing a little lump of material here, and I'm going to make that concrete. So what I can do is materials here, I can simply drag and drop them onto the body there, and what I'm going to do is replace this material here. I don't want material R2, I'm going to use my pre-modeled R1 material. So that's the one that was embedded in the block at the front, so that means it won't pull out of there. If I click there, so effectively now I've got a soil nail with a big lump of concrete on the end. Now I can keep the soil nail with its same interaction properties, pull-out factor of 10. If I want to model it with no interaction with the surrounding soil, so if it's a very narrow tendon or small tendon, I could make that a smaller value, but the element is still able to transmit tensile force. I'm just going to remove the top boundary of the soil here just to give it somewhere to go. So if I click solve here, hopefully what will happen is that this will pull the block out and give me a failure mechanism. So yeah, essentially it's pulling that anchor block out. We've got a constant axial force along here, which is effectively the force required to pull that out, and we've got a failure mechanism around the system. So that's kind of rough and ready, but it shows another use for these engineered elements. Okay, so I've got a question. How does one draw or enter the reinforcing elements, and do you have to draw the line around the zone of reinforced soil? The easiest way to illustrate that is to pull up, for example, a slope stability problem. So in the software, if you haven't seen it before, there's a number of quick create wizards which generate standard geometries, but you can change those as you wish. So here I have a slope actually in clay. If I wanted to put a soil nail in here, engineered elements are modeled essentially on boundaries, which separate different bodies of soil. So the easiest way is to draw a line here, for example, and then up at a vertex at some point, and then if I want my reinforcement to act on that line, then I would apply it to that. So having selected that boundary, I can assign a property to it. So I can assign an ordinary soil property, and that's useful for modeling, say, pre-existing slip surfaces. But in this case, I'm going to pick, well, we have one predefined soil nail element. Of course, you can specify your own properties, but essentially, I've now assigned that to there, and then I can click solve, and that element will affect the failure of the system. So that has forced a mechanism to go out there. In order to show that, I'll remove that element. If I click this undo button, it will undo my changes, and I can show you what the failure mechanism would have been without that element. So that's a different failure mechanism. So we can see that that element has actually modeled that. Okay, I've got a question. Can the software model secant or contiguous piled wall problems? It's essentially, this engineered element can also be used to model sheet pile walls, which will have an analogy to secant or contiguous pile wall problems. So if you can specify that problem in terms of your piles having a particular bending strength or a particular strength, this is effectively what we've got here. This is modeling a sheet pile or a continuous piled wall, and the element, the engineered element in this case, we can specify a moment of resistance, so it can have a bending strength. So if you exceed that bending strength, whether it's steel sheet pile or a concrete contiguous pile, then that element will bend. So you can use these elements to model that type of problem. If I click solve here, it's set up a particular default geometry and soil type. It's able to model a tension crack here, and it's what we have displaying down here on the element is now the moments on the wall. But just to show that we can model bending, if I set this to a very low value like 5, then what we should find is that the mechanism of failure moves up, and that the wall itself then suffers bending collapse at this point here and stays rigid down here. So it is possible to model those aspects. Okay, we've reached 10 o'clock, so I'm afraid I'm not able to answer the remaining questions. So apologies that we didn't get through to those ones, but we will reply to you with an answer to those questions. So I'm going to pass back to Tom just to wrap up. So thank you very much for your attention and hope you found that useful.
Thanks, Colin, and thanks to everybody for listening this morning. So we're now at the end of the webinar, and we do hope that you found it informative and interesting, like I say. For the people who are current users of the software, we hope that you did learn something new about it that maybe you didn't already know. And if the webinar, as we said, has prompted any questions, then do get in touch with us via telephone or via info@limitstate.com, and we'll be more than happy to help. For those of you who aren't current users of the software, we'll be in touch probably tomorrow morning just to get some feedback to find out whether you've got any further questions and see whether you think LimitState GEO would be useful for you. If you'd like to watch the webinar again, I know it came up in the questions just now, there will be a recording available probably later today or early tomorrow morning, and we'll send out an email with a link to that. It will be on our YouTube channel, which is youtube.com/LimitState software, where you'll be able to see that and also all the other LimitState GEO webinars that have been recorded for the series. You may also be interested to know that there's a number of other scheduled webinars that deal with LimitState GEO, so please do keep a lookout for those. We'll be sending out event notifications, and they'll also be posted on our website at limitstate.com/events. So again, thanks to everybody for listening, and hope you can join us again for one of our future sessions, and we hope to see you there. Goodbye.